Okay, let's continue again. Here's a summary of what we have learned. So I showed you how from the landscape of a free energy function, a density, you can construct when the system is unstable or stable against small or large perturbations. We found that there's a concave region corresponding to an unstable regime between the spinodal, and then there's a metastable regime between spinodal and binodal, where the system still phase separates into two domains, but needs a finer perturbation. And then outside of it, so here and there, and this in the phase diagram, you have a stable regime where the system mixes just fine. What we saw is that we have this famous common tangent condition by Maxwell, where the derivatives of the free energy are the same, and this object here is the same, giving you the same line. And then there is this condition, the lever rule, that restricts you to the case where you have the volumes the same and the particle number the same. Now, what we don't know yet is what does this actually mean? What's f prime in terms of some physics, and what is this object here in terms of some physics? And let me start with the latter one and talk about an important concept in thermodynamics, which is the osmotic pressure. Yep.
So, one question about
this. Please go ahead.
This. So, once we enter the unstable regime, what exactly means where we are on the line?
So, you mean now what?
Like when we fall that.
So usually you're somewhere here because you're in thermodynamic equilibrium. So let's say you are here at temperature T and volume fraction phi. So let's say we start here. And now I drop the sample into a very cold environment. Let's say I drop it down to this point where the average volume fraction is still homogeneous, but my temperature is much lower. Then your starting point would be, say, this point here on the free energy landscape. And then, as this point is thermodynamically unstable, there's some dynamics going on, which will push you away from that state. And then the system will ultimately relax in the long run to a steady state where it's demixed with the concentrations given by phi A and phi B. I'll show you a movie. Maybe this shows more than 1,000 words here. Right, so here in this movie, this shows you the phenomenon dynamically. So as we restart it again, this is kind of an initial condition, which is basically homogeneous with some small perturbations. The different colors you see are in a very narrow range of concentration differences. So it's basically this quench I was talking about, that you start homogeneous. And now that state here is unstable. Any small perturbation, as you see them, drives it away. And then dynamics sets in, and the system demixes into a region that's high in concentration, a region that's low in concentration of the solute. And this goes on and on and on until ultimately you'll have a state with a single droplet of the red density region here in a domain of blue. Okay. And this final state is then the one that corresponds to the common tangent construction in the Maxwell construction.
Okay, but for those two states, phi A and phi B, I can have different proportions between them, right?
No, they're fixed. Phi A and phi B is fixed by the Maxwell construction.
But I can have like more phi A than phi B, for example, right?
What do you mean by more?
That like there would be a
The volume fraction of it, the volume of it.
bigger drop of quantum mechanics.
That's defined by, if we go back now, there's still this rule here. Okay, so you have phi A and phi B, they are fixed by the construction, but the amount VA and VB is variable, because that depends on this lever rule. This combination here needs to be obeyed. Particle number conservation and volume conservation. And that then determines how much of the volume the phi A phase takes and how much the phi B phase takes. Right? Now, so let me come to the interpretation of this condition here. What's an osmotic pressure? I assume you know that, but let me recap anyway. So imagine you have a wall, and this wall is not fully permeable. It's permeable only for the solvent, but not for the solute. That means if on one side of your system you just have a mixture that contains the solute, and on the other side you don't, then there will be a pressure that you need in order to keep this wall at a steady state. The argument is as follows. You will have to perform work against this osmotic pressure that's acting from this side of the volume to the other side. This is the work you perform. Okay, it's the work performed that will change the free energy. Total free energy. And the total free energy here in this case is the free energy density of my left volume. So this is volume V. The whole thing has the volume V total. So here I have a solution, and the other part is the total volume minus this, and here I have no solute molecules. Okay? That's the total free energy. This is the work you perform, and the pressure, this osmotic pressure, is then given by the partial derivative of this total free energy with respect to the volume. Okay? You can do the calculation because we know the expressions that we have there. We know F total, so we can take the derivative. And this is then minus F of T and phi. And now I reintroduce the T plus phi, F prime of T and phi, plus F of T and 0, where I have used that d phi df, the volume is minus phi over volume. Okay? So now you see that this object that has a clear physical interpretation, it's the pressure acting on a semi-permeable wall. That object is what's balanced in the second part of our Maxwell construction. Here you see this is the osmotic pressure that corresponds to the system composed having a volume fraction phi A, and that's the osmotic pressure of the volume fraction containing having the volume fraction phi B. So the osmotic pressures of these two final objects, they need to balance such that you have a stable state. So it's kind of a mechanical equilibrium that you need to have in order for the system to be in a stable state. Okay, so what we have is that pi of phi A needs to be pi of phi B, equal osmotic pressures. We can think about this osmotic pressure a bit and ask ourselves what it is. Now, without doing calculations, let's say we measure things. And there's a famous measurement by Van 't Hoft that specified how this osmotic pressure depends on the volume fraction of the solute molecules. And what he found is that this is proportional to phi times the temperature scale. And to make the units right, this is divided by the molecular volume of the solute particles. Okay, so the osmotic pressure measured is linear in the volume fraction, and that's called the Van 't Hoft law. You can go further and say, well, let's consider what happens if you would have higher density, and then this is modified. So that's just the Van 't Hoft part, but there's other parts that come to it, and you just say, well, this should be some power law in A, in phi squared, or phi to the third, plus etc. And these are some coefficient, A2 and A3, that modify Van 't Hoft's law if you go to higher densities. So this is obviously something which is evaluated at a low density, and these are natural corrections that can appear at higher densities. You can think a bit heuristic about what should happen with these higher order coefficients. So as you have in the system not just a very dense, a very dilute solution of particles, but something that becomes denser, right? Then you have interaction between the particles. If the interactions between the particles are attractive, then they don't push against the semi-permeable wall. So attractive interactions between the particles will typically lead to a lowering of the osmotic pressure. So A2 you expect to be negative for attraction between the particles, just heuristically. All right, now you can write the formal expression that we have here, this osmotic pressure, also as follows. You can write it as phi squared d d phi f over phi plus f of 0. And you can do it for yourself. Just take that expression and check that this one here is equivalent to the above definition of the osmotic pressure. The reason I'm writing it like so is because then you can read off from this power law expansion of the osmotic pressure, you can read off the structure of the free energy density just by integrating this relation. So and as you do, as you integrate that relation, what you do get is a constant plus a linear term, and K0 is an integration constant, plus kBt over Vp phi log phi, that's the 't Hoft term. And then we have plus A2 phi squared plus a half A3 phi to the third, etc. Okay. Yeah.
Are those A coefficients also dependent on temperature?
Yes, in general they are. They depend on molecular interactions and temperature, etc. I don't calculate them for now. I will do later. So at this point, they are phenomenological coefficients. in a similar fashion as the reduced temperature or the R parameter in model A for the Ginzburg-Landau theory. You can calculate them. This is a standard exercise in thermodynamics, often not taught. It's called virial expansion. If you do a virial expansion for a thermodynamic system, you can calculate A2 and A3 given that you have the interactions between the particles known. Okay, I'll later come to calculating A2, right? We'll see that. But for now, I really want to emphasize that phenomenologically, without going into molecular details, from measuring these osmotic pressures and their dependence on volume fraction, you can infer the thermodynamics of the system, the free energy density. And that has a structure like the one I drew, because that's just the natural way a polynomial of third order looks like. Good. What about the other condition? The first one. And for that, I need to introduce what's called chemical potentials. And I'm sure you heard about this, a chemical potential. And actually, we defined it before as a function of temperature and pressure is given as the partial derivative of the Gibbs free energy with respect to particle number, keeping the other thermodynamic parameters fixed, which is the number of solvent molecules, temperature, and pressure. That's the definition of the chemical potential, and that was reflected in me writing dG is the sum over mu's times dN. Now that we have this particular expression of G being V times P plus the free energy density, we can also write this in this form. This is Vp, pressure plus free energy density plus 1 minus phi free energy density prime T of phi. And we can write the corresponding expression for the solvent in the same way. dG now with respect to the number of solvent molecules, the solute molecules being fixed, temperature being fixed, pressure being fixed. And this is then Vs, pressure plus F of T phi minus phi F prime of T phi. You can rewrite this expression a bit. So if we use the definition or the expression for the osmotic pressure here, this relation, then the second relation can also be written as Vs times P minus P of T phi plus F of 0 and T. All right. What you should notice is that these quantities, and that's of course correct, they are defined with respect to constant particle numbers of the respective other species. What we want here is typically not this. We are looking at a system that has constant temperature, constant pressure usually, and also constant volume. We don't change the volume really. So we want to have these expressions as a function of constant volume and not constant particle number. And they are called exchange chemical potentials. they are defined as mu p as a function of temperature and volume fraction. That's then the partial derivative of the Gibbs free energy with respect to particle number, but now keeping fixed volume, temperature, and pressure. And then when you do the calculation of that, and I spare you of this, it's really very trivial, you get Vp f prime of t and phi. So this exchange chemical potential is exactly what you have here at the first line of our Maxwell construction. The chemical potentials of the two phases, A and B phase, they have to equal, which is the common tangent condition. Right? And the other one, mu s, so it has to have a bar to indicate that this is the exchange chemical potential. Here, the same thing, defined as dg, dns, volume, temperature, pressure, and then that's just minus vs f prime of t and phi. Good, so now taken together what this means, our purely geometric construction, where we only used that we have to find the lowest free energy state leading to Maxwell's construction, has the interpretation that the chemical potentials, the exchange chemical potentials in the two phases need to be the same, and also the osmotic pressure of the two phases need to be the same. And you can use this in an alternative fashion, right? You can say this is the Maxwell construction that gives you the equilibrium state, or you can say this is my condition on chemical potentials and osmotic pressure, which then yields the Maxwell construction. I like it the other way around because this is a fundamental thermodynamic principles, and that's a derived interpretation of the objects we study. Questions?
Could you give some more intuition about like what do
Exchange?
How to think about this exchange chemical potential?
Yeah, see, if you don't do exchange, you keep the particle number of the other species fixed, which is very unnatural. Right? What you do is you exchange particles in this solution, keeping the volume fixed. And that's what you want to understand. You want to know how much you change the Gibbs free energy by changing the number of solvent or solute molecules in an environment where the volume is fixed, but the rest can exchange as it likes.
Okay, so for example, in a cell, we have a fixed volume, but
exactly.
You can have like any fraction of like water to
proteins that you produce, for example. Right? And you want to know, say, you produce an extra protein, or an extra amount of proteins, and you want to know how much chemical potential does this generate.
Okay. And typically you would have just a system that
has a constant
cannot produce any more solvents or more
or less, right? It can add stuff, or proteins can be degraded. There's a lot of different processes that can happen, but the volume is, in most of these systems, a constant. Even in other chemical systems, you don't change the volume much. It's a container in which you make the experiment. That's not what you're interested in, and you want to keep that fixed. That's your natural choice of boundary condition. And when you make this natural choice of boundary condition, then the chemical potential is the same as the derivative of the free energy. And all you pay then is how you walk on the free energy landscape. So a gradient in free energy gives a chemical potential, right? And this chemical potential then is the driving force of the dynamics. And when you remember what we did for model A, where I just wrote down the dynamics saying that the dynamics is something that contains the gradient of the free energy being the chemical potential, that's basically the argument. And you'll see here in a second. So if you wait for me writing down the equation of motion, then you see again why this is the key variable to look at. Okay, now let's talk about thermodynamic driving forces and non-equilibrium currents. So we want equations of motion now. That's going beyond thermodynamics. We're now interested how the time evolution of phi really happens as a function of space and of time. So I would like to know what is the time derivative of this object. First thing I have to realize here is that solute particles and solvent particles are conserved quantities. They don't just pop out of anywhere. They are redistributed in space. So the dynamics of the solute concentration needs to be a conservation law. So I have to write this, there's no other choice, as a continuity equation with the divergence of a current of x and t. I don't know the current, but I know there must be a current that I can define, and this then gives the continuity equation. This continuity equation, because we have particle number conservation here. What's the current? That's the key question. What should I write as the so-called constitutive equation? J of x and t. Now, what did we learn? We learned before that in thermodynamic equilibrium, the two domains with the A phase and the B phase, they have the same chemical potential. So in general, the system wants to relax to an equal, homogeneous chemical potential everywhere in space. On the other hand, this means if you have a gradient, the system is not in thermodynamic equilibrium yet. So gradients in the chemical potential are driving forces for currents. And with mu, I now mean my exchange chemical potential for our particles, for the solute. Okay? They are the driving forces. If they're gone, there's no current. And the assumption of non-equilibrium thermodynamics in the linear regime is that I can write this as a linear relation between the current and the gradients of the chemical potential. If I were to consider higher order terms, I could add higher order gradients if I like. But that's certainly the lowest order term I have to write. Okay? So to lowest order, in the gradients. And then, as in all these phenomenological considerations, there is a proportionality constant that we call lambda. I know the sign. Because I want something that relaxes gradients in the chemical potential back to equilibrium. So this must be minus, otherwise I amplify gradients. Okay, so I know this is minus a positive constant, and they are called Onsager coefficients. These Onsager coefficients, they don't have to be constants. They will in general be functions of our variables. So This can depend on temperature, and of course it can also depend on our dynamic variable, which is phi. And we don't know this a priori, because all we put in here is that systems relax driven by gradients. Okay, so these are the thermodynamic driving forces. And this is really very, very general, because in many of these non-equilibrium situations, the way you argue is you are driven back to thermodynamic equilibrium by gradients in various intensive thermodynamic quantities. The chemical potential is one of them. There are other quantities that are homogeneous in steady state. So when you have a more complicated system with more variables, not just scalar quantities, but maybe vector quantities, similar arguments apply, and you can construct for, I guess, basically all problems close to thermodynamic equilibrium what's called an Onsager theory for the relaxation back to thermodynamic equilibrium. And this here is our simplest paradigmatic case. Okay. So what we know already is these derivatives, or the chemical potentials. And what I need then, if I take the gradient here, I'll need the derivative of mu p with respect to phi. And let's look what this is. Right, mu s or mu p here, they are proportional to the first derivative of the free energy density. So as I take a second derivative, I'm getting also the second derivative here of my free energy landscape. And for the solvent, same thing. As I take the derivative, I get minus the specific volume times the second derivative. Okay, now that we have this, I can write a more explicit expression of my non-equilibrium current, because now I can rewrite the gradient of mu as a partial derivative of mu and a gradient of phi, which I want because I want this equation to be closed in an equation as a function of phi. So that's then minus a constant, the molecular volume, lambda of phi. I'm just omitting here the temperature dependence, f double prime of phi, gradient of phi of x and t. Okay, and now you see again our instability criterion. This is a current. The current is proportional to the gradient of phi, but the prefactor defines the sign. Here's a minus. Vp is a volume, it's positive. Lambda, already argued, is positive. But the second derivative of f can change sign. It can be concave or convex. And as it changes sign, you change the sign of the current. The current, if the system relaxes back to equilibrium, has to be such that it's minus a positive constant and the gradient of phi. Then it relaxes back to a homogeneous steady state. If the sign is such that the prefactor is positive, you amplify perturbations. Okay? Or think of this just as Fick's law, right? Then this is a diffusion coefficient. Diffusion coefficient needs to be positive to things to relax back to thermodynamic equilibrium. If diffusion constant is just having the other sign, you get the opposite behavior. All right, so that means for f double prime greater than 0, this is stable and you relax back to phi equal constant. And in the opposite case, you get an unstable situation that must lead to a deviation from the homogeneous state, and that must lead to demixing. We know this already, right? This is what we learned from thermodynamics, but we recover it here in the dynamics of the system in an explicit way, that the dynamics itself shows this instability. Now let me use what we know to fix the constant here, the lambda. So say we have Toft's law, van Toft's law. I think I still have it here. Right, so if we just have Van 't Hoff's law, then our expression for the free energy density stops right here. Okay? The other terms are coming from interactions. This is the low density expansion that we get. So if we have that, and we take the second derivative of phi, then you see this will be gone because it's a constant. This will be gone because it's linear in phi. This will not. That will be the only contribution you have. And this will give you kBt over Vp times 1 over the volume fraction phi. Or in other words, in this limit of a low density system, the non-equilibrium current that we have will be such that you have minus lambda of phi divided by phi kBt gradient of phi. In the low density limit, and it's now key for you to realize, what we have here should reduce to some other law that's very well known and established, namely diffusion law or Fick's law. So this must be the same as minus d times the gradient of phi, where d equals the diffusion constant. As a phenomenological macroscopic input, right? Something we know from the analysis of many different low density systems. So from that you infer that this Onsager coefficient has actually a dependence on the volume fraction, and it is given by d over kBt times the density phi. Now, question to you. Diffusion, we heard about this. I think Bea talked about this. It comes from what? It comes from the irregular motion of Brownian particles. It's nothing but the expression of temperature acting on the motion of particles, right? So it's nothing but entropy. There's no interaction in Brownian motion. It's simply the action of entropy on particles. So Toft's law, in retrospect, is an entropic force. It's just encoding the fact that in a volume where you have a semi-permeable wall with some solute particles on the left and none on the right, there's an entropic force pushing the wall. This is what Van 't Hoff's law is. And that's something we see here in retrospect because this is matching to the to Fick's law. All right, I think I stop here. To wrap up, what should I say? No, let me stay here. So how far did we go? I showed you this. This is thermodynamics alone. And then I gave you this line of argument that shows the dynamics. And this will us now help in the next lecture to use these dynamic equations together with the form of the free energy density to learn how the phase behavior in these systems is, or how you actually go from a homogeneous state and demix. So in the end, these equations are underlying the phenomenon that I showed in between that you see here, where you have demixing phenomena. These equations here that you see here describe what you see here on the movie. They are basically a finite element solution of the equations of motion that you see. And what we want to learn is how this happens, not just solving a differential equation, but more than that, what we want to know is what's the dynamics again of those lines that we see here, and how can we relate those to the partial differential equations defining the density fields. Questions?
Yeah. Between the binodal and binodal region and with the small q of F as a potential barrier for this mass level region to be unstable?
Yeah. So what you need to do is, if you're here, in between, you need to make a large enough perturbation here in the center for the system to actually nucleate a droplet. Right? When you know this from experiments, I think we all have heard lectures on particle physics, right? Where you observe elementary particles in chambers which are in a certain state, and then these particles, they leave a trace of droplets. That's basically that phenomenon, that you have something that needs a nucleation, something that causes the nucleation of these droplets. And you by purpose put it in a regime of the phase diagram such that only if you have a perturbation, you see the formation of droplets.
Maybe my question to be more precise, like the perturbation is sensible to a global landscape of many.
It's a very difficult problem. Nucleation is a super difficult problem because that's subject to all the details of the system, because you need to know what the barrier is and how you get over the barrier. That's a very complicated physics problem. The other ones are much easier because they're more generic and universal, while nucleation has a strong dependence on molecular details. Yeah. No?
Please. So in the end, when we argumented that this on-cycle coefficient should have certain form, so we phenomenologically expect that for low concentrations we should get diffusion equation, right? Mm-hmm. So this demixing phenomenon, we expect that it should happen only when we add those A2 or A3 coefficients.
Yeah.
Okay, so without those there would be no mix.
True, because you're right. So in this limit that I use to fix the on-cycle coefficient, like so, if you plug this in, you get diffusion equation, and diffusion equation makes a flat state. no pattern formation, no droplets, no coarsening, nothing. So you do need the dependence of the free energy on higher order terms. So you do need, as you say, A2 and A3. You need interactions, because without interaction, you're just dominated by entropy, and entropy makes mixing. And this here, this phi log phi term is mixing entropy. Right? Think back of binary mixtures you studied in thermodynamics, maybe a year or two ago in your undergrads. The mixing entropy has exactly that structure. And what you want, right, is that things attract, and that gives rise to demixing. So the A2 here also has to have a particular sign for systems to demix. Otherwise, your landscape will be different from a harmonic landscape. It will be nonlinear in a way, but it will have no minima. And from the Maxwell construction, you see, so here, for example, you need those minima. They are essential. Otherwise, you don't get phase separation. Great. Then have a nice rest of the week and see you next week.